Over a year ago, I left people with many questions about gravitons with my first video on them. So in this video, I'm gonna recap more clearly what I said and expound a bit more on the subject. In order to understand gravity, we need to start with the simple classical mechanical explanation. In classical mechanics, we have two famous theories. The first one is the Newtonian version of gravity proposed by Sir Isaac Newton, which simply states that gravity is caused when two objects exert gravitational attraction on each other. Then came Einsteinian gravity, which is the currently preferred view of gravity, which shook things up a little bit, claiming that space and time were interwoven into a single entity called space-time, and that the presence of an object distorted space-time, and that it was this distortion that we perceive as gravity. However, the problem with the classical mechanical explanation of gravity is that when we try to understand gravity on a quantum mechanical level, our classical mechanical view breaks down and fails to comprehend what gravity is on a microscopic scale. Then in the 1930s, two Russian physicists proposed a theory that would garner a lot of interest. This shocking theory stated that just like how the electromagnetic force is transmitted through the exchange of subatomic particles called photons, the force of gravity was transmitted by a hypothetical subatomic particle called the graviton. The graviton can be explained by another theory, string theory. To sum it up, string theory is a controversial theory, stating that all the matter in the universe is made up of tiny, vibrating, one-dimensional particles called strings. Strings can fall into two classifications, open and closed. Open strings, aka the matter you and I are supposedly made of, are permanently attached to our universe, which the theory suggests is a giant entity called a brain. Closed strings, on the other hand, aren't attached to our universe and are free to travel to other universes if they exist. Gravitons are supposedly theorized to be closed strings, which means they can leave our universe or brain since they aren't attached to it and travel to other universes or brains if they exist. In other words, one way to detect gravitons is to check for gravitons coming from other universes, but this is a highly unviable option since other universes probably don't exist, and even if they did, they are billions or possibly trillions of light years from Earth. This whole distance thing poses an issue because contrary to popular belief, the speed of gravity is not instantaneous, but rather gravitons are calculated to travel at the speed of light. And while the speed of light is undoubtedly fast, it is still no match for the vast distances found in the cosmos. Going back to what I said, general relativity is good when it comes to explaining the realm of our everyday life, but on a quantum mechanical scale, it is utterly useless. So the ultimate question to be answered is, do gravitons succeed where Einstein failed? Well, the answer to that question is not at the moment. While gravitons offer a nice explanation of gravity, we are yet to discover their existence. So what exactly is it about gravitons that makes it so hard to discover? You see, gravity, contrary to what many people believe, is one of the weakest forces to exist. In fact, the bonds holding together a hydrogen atom are stronger. Another example to prove my point is how easily I can pick up an apple, despite the entire Earth exerting a gravitational pull on it. From a quantum mechanical view, the reason for gravity's lack of strength is due to the fact that gravitons interact very weakly. So as a result, detecting a graviton would be very difficult. Referring back to classical mechanics for the final time, while the theory of gravitons may not do what general relativity couldn't, general relativity did give scientists a nice starting point. According to general relativity's explanation of the distribution of the mass and energy in the universe, if there is a graviton, it's a massless particle with the spin of 2. Scientists from Fermilab to CERN are looking for this particle with eager eyes in the physics community, but until we find and confirm the existence of gravitons, they just remain a theoretical explanation of our universe. If you enjoyed this video, be sure to leave a like and subscribe for more science videos. Also, with all the recent discoveries and breakthroughs in the field of astronomy and quantum physics, if there's anything you'd like to know about, be sure to tell me in the comments below. And in the meantime, stay tuned for more science.